the surface is quite hard and have a different property? Is it possible? If so, how? Clearly. Say that. So you're going to pour up to here, and then you're going to change a different pour. Is that? Okay. Are you suggesting to pour here, or pour this entire? So it's up to you. And I mean, you're pouring the concrete up. If the exposure is on the top, you can pour up to here, and then you can pour after that. Yes and no. Yes, because then theoretically, yes, that's a better, much better concrete. But no, because you're now creating a bonding layer right at the rebar interface. We don't know how they differently expand, or we don't know how they bond, and also how fast is the first layer to the second layer, because you might actually have a construction joint right at the critical interface. So, and in reality, that's nearly. I mean, you rely on somebody on site to do that for you, to a theoretical precision. It's not site adaptive. Anything else? So after the concrete is cast, you can put a coating. You mean? Okay. 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 These the anodes that we talked about, you can install the anodes in the concrete at the time of casting. So if you're looking for corrosion to be prevented, and you know the structure is critical, you could consider anode installation even at the beginning of it. Let it be there, and it'll do its job when needed. Okay. Tricky, because you need to design the whole thing and also to place the anodes carefully. There is another material called controlled permeability formwork liners. Have you come across that before? So most of the concrete is poured on impermeable surface. Alright? It's either metal, mold, or timber. Are there any plastic molds here? Yeah, plastic mold is a good thing. You should not consider plastic molds. Anyway, you get like a very glassy finish. So it's impermeable surface. Yeah. I'm going to cast let's say I'm going to cast a beam, and I know this is a critical beam for my structure, so I'm paying a bit more attention. So made a timber mold, and I'm going to pour the concrete in. So there's a lot of rebars all over the show. I'm sure it's very complex, these things. The liner works in a very simple fashion. So what it does is it creates a material here like a mesh. Okay, so it's very similar to the clothes shopping bags that you have. Okay, it looks very similar. It's a bit more thicker, clearly, and it has two directional grooves in it, inbuilt. So because of the holes in it, the water on the surface will run into the grooves and they will get out. So you'll need to find a way of draining them as well. Okay, and then you will have the mold sitting next to it. It'll be very flush, and these are maybe 2 or 3 millimeter thick, very strong liners. Okay, so the grooves in it's designed that it'll let the water out quickly. It's permeable. What happens is when you pour the concrete into it, the excess water on the surface in contact with the mold will drain off. Okay, the pores are small that it doesn't let the cement particles out. In theory, I'm sure it'll let some amount of cement particles out, but it won't be much anyway. So it'll basically get the excess water out. So the net result is the water cement ratio here will be what you designed. The water cement ratio here will be much less than what you designed. Okay. Effectively, you got a cover concrete of varying water cement ratio, this being what you designed and this being the lowest. And that gives you the extra protection that you need. It's a very simple liners that they use. The technology was developed 25 years ago. Okay. It's commercially available, I think, all over. There's a lot of companies manufacturing it. I don't know if anybody in India is doing it. I know they use that extensively in China. It's something worth considering if you are looking at a very critical support, and you can reuse that. I think we did a lot of work for them then, before my time. They wanted to see how many times can you reuse this, because you're investing clearly. And they figured out that 3 to 4 times it doesn't change its property. I don't know what happens after the 4th time. Okay, I'll write the name for it. Okay, it's control permeable deformer liners. Google it. I'm sure you can Google it and you can get it. And it's produced in China, so I'm sure you can get it really cheap. So, where are we? So, the person, it's my predecessor who took that picture and decided to add that into the presentation. I should also say about the presentation slides. These slides were put together by a professor called Mohammed Bashir, and I inherited them and I actually adapted them for my style of it. And as everyone puts it through, he can go through the slides quite fast. He's a very effective teacher, but he often says that I take the slides, or the Mickey of the slides. I use the board more than the slides, so slides are just a guide for me. But unknowing to him probably then, the expression of genes to be a protective lining has a meaning with the control permeable deformer, because they are quite a designed material and they can let the excess water out. Okay, but the intention was that you create a surface layer. Okay, that you can do by coating with some form of waterproofing material, or you can coat it with a curing compound. You can use a control permeable deformer liner, or anything that benefits, okay, or anything that's more locally available and adaptive. Okay. Nature might have a control permeable deformer, so you can look at that to see. Those who are into the environmental side of engineering can look to see what similar compounds does nature provides. Okay, you know the banana skin. Okay. Sometimes some kind of banana skin might have the kind of grooves that you're looking for. I'm not leading anything, okay, I'm just suggesting. So look that under the microscope, see if any of those kind of skins that are normally a waste material have the property, and then you can use them. Okay. If you're working in research. This is what we do in research. We have the luxury of time to look at things at a slower pace. We're not like industry in that sense that we're not going fast. So yeah, that's that. The other thing I wanted to say is freeze-thaw, but I wanted also to ask, is freeze-thaw an issue here at all? Maybe not in the south. In the north?
Not a freeze-thaw, but it's a lot of cold.
Okay. Freeze-thaw, for those who understand fatigue, freeze-thaw is very similar in its action. It's the number of cycles. it's a number of cycles where your temperature goes up and down a particular value. Okay. For easiness, we can say 0 degrees, but I don't think 0 degrees is very critical. Could be a bit below that, or could be above that even. So these, I'll explain the mechanism and then we will leave it at that. So the damage will look very similar to a chloride damage, because freeze thaw quite often has salt coming into it. You can have freeze thaw with water, okay, but it'll be much more faster if you have chlorides in it. Partially because chlorides have the ability to reduce the water. Assume it that way, that it basically changes the surface tension, but it has the ability to make water go everywhere faster. Does your dishwasher tablets, does it have salt in it?
This doesn't.
Okay.
Well, nobody uses it.
Sorry. So the water, the surface tension of water reduces when you put salt in it, which means it can move around things faster. If you look at your Surf Excel, they might say somewhere it's ionic particles or ionically charged particles in it. Okay. It's designed so that it can go, the surface tension can go as low as it can, so it can get into the fabric and remove it. Okay. It's clever engineering. Okay. You can, if you have the luxury of time, look at the particles and see what, I don't know whether they even publish any literature, but they'll probably never publish anything. But it's known even to react with the dirt and oxidizes it and lifts it up. So it's a very clever engineering. There's a lot we can learn from the chemical companies. Okay. So it'll look very similar to chlorides, but in the flat surface like car parks, what you get is called pop-outs. The early sign of it is a pop-out. So there might be a cavity below the surface, and the cavity gets filled with water. Temperature goes below 2 or -5. Then that cavity which is filled with water just expands, and that expansive force have to be accommodated by the concrete. So weaker concretes will tend to crush the pores and be happy with it, but stronger concretes tend to do pop-outs because it has no way to take that force. It'll just lift it off. Okay. So if you're seeing pop-outs, it means this concrete is reasonably strong, but it has cavities in it. Okay. It can be very extensive. These cavities are connected, which means the whole layer is filled with water, and then it can be very extensive failures. Okay. Progressive as well. Obviously, it'll affect hydraulic structures because their access to water is very critical. Okay. So this is an illustration of how it works. So the capillary cavities get water into it, and as the water expands, the cavities will have to rupture in order to accommodate that force. So dilation. And this is the pop-out I was explaining. Okay. So if you look at freeze thaw damage in pores, you can see cracks everywhere. This is I think it's a visible normal picture. And it's very extensive. It just ruptures the whole stuff, so the strength will be gone. And you can also see in the structure that you have cavities everywhere. You have holes in the structure. So it's a weakness of the structure that it make use of. The answer to that is also in cavities. So it's called the air entrained concrete. So you forcefully put air entrainment within the concrete. You get a chemical that you can buy these days called air entraining admixture, and it'll create air bubbles at a distance. Okay. Once again, that is a clever piece of engineering. If they are dispersed, that means when water comes in, water can just rest in the pocket. And the density of the concrete will be the other factor that you can control. So you make the concrete really good. You put air entraining if you expect freeze thaw to happen, which means if water comes in, it has expansion pockets in it. Okay. It's not an ultimate protection. Your ultimate protection is reduce the rate of ingress of water, lower the diffusivity. You might see a theme evolving. Lowering the diffusivity is very critical in durability. This is how it looks if the air is dispersed quite well. Okay, so yeah. So the ultimate part is cracking. Once cracking is there, then the salt can come in and do the job, finishing it off. Okay. The other option is to reduce its moisture content. Okay. Now again, we looked at corrosion. One of the things was to keep the moisture away and keep the concrete dry. In this case, it's the same. If you can keep the moisture away, you're good. So what treatment can you do for concrete that has freeze-thaw issue? Get the water out, waterproof the surface. Seems to be a common thing, get the water out, get waterproof the surface. You have to get the water out. That's not easy. So you'll need to apply waterproofing that'll let the breathing out of the concrete. So it has to be breathable. If it's non-breathable, you're basically locking the problem in, which causes even more of an issue later. Okay. So the best form of protecting concrete, can you summarize the best form of protecting concrete? If you had the luxury to start new and you had to create a concrete that'll last forever, remember it'll never last forever, but let's say it has to last forever, you have to create the concrete with the lowest diffusivity as you can. Okay. When I say the lowest diffusivity, I don't intend by any means to say the lowest possible, because in doing so you're affecting the structure tremendously. You should only go if you're looking for monumental structures in that direction, and you need to do a lot of R&D before they're site worthy. Okay. But a lower diffusivity is a good starting point. Okay. The second thing is, British used to say, keep your powder dry, reference to the gunpowder, the same as your concrete. Keep your concrete dry if you can. Okay. Keep the exposure environment away from the concrete, surface coating, tiling, anything. Okay. If you expect further problems for the structure, use technology that will help you with that. So these are the common things. The one thing I didn't mention is carbonation. Carbonation affects the concrete that will be faster in a concrete that has humidity about 65%. Okay? Which means if you keep your concrete very dry, it's good. If you keep your concrete at a moderate humidity as that, it's not good. So to avoid carbonation, flood the concrete if you want to. 100% saturated. For CO2 to go into liquid to form carbonic acid and then to go in, it's hard work. Not going to do it. But 65% humidity means that's ideal for it to carbonate. So again, if you're dealing with structures that are about to carbonate, keep it dry, very dry, or keep it moist. Keeping it moist is not a solution because you might be inviting other issues. If you keep it fully moist, chlorides will find it easy to get in. So it's not an easy material, So that brings me to alkali silica reaction. Okay? What time is it now? 53, 8, 9, 9:30-ish. No, 10:30-ish. Okay. Right. We're going to take a break, and I have a reason for it. After that, when we restart, I'm going to show you an example of a pile that we had done as part of a consultancy. So I'll just bring you to a case study. Example of what we expect. It has no deterioration, but we were looking for deterioration to decide whether those piles can be used. Reusing piles, for those in the industry, knows it's a big money. That means you really don't need to do anything, you just get going with the structure. Provided you know you can rely on them, because that's fundamental to the structure that your piles remain. Okay. So we did some work for that, and then I can explain that afterwards. Okay. Yeah. Okay. Oh right. Okay. We'll do that then.
If I look at any building, No, generally you think about the white red patches coming down from the bottom or side of the building, which may be related to the erosion.
Okay.
Now we are after erosion, we are classifying the erosion into carbonation and the fluorination. How can distinguish the visual inspection? It may be reduced by chloride or carbonation.
Okay. Visually, it depends on your bird's eye view. Okay. So a structure is standing, but before I answer that, by no means my answer is going to be complete. I'm sure the others can complete me in staying that in completing the picture. So if a structure is standing and you're getting corrosion in a particular side, the question is whether you can have a larger view of the structure. So